This is CS1101 Lecture 6.3. We're continuing our discussion of loops, and we will also be introducing ciphers, a very simple cipher in this lecture. So we left off last lecture with an aside, but before that we were dealing with this program to be able to print a mirror. And we had written a method for drawing the top half of the mirror, and we said that the bottom half of the mirror was only different in a very trivial way from dealing with the top half. So we had fully defined how to draw this mirror more or less with gaps that we would expect that you would be able to fill in. But an extension that would be pretty helpful to this program for drawing mirrors would be a way to draw a mirror that had the right size. So the left figure has size 4 because the top has 1, 2, 3, 4 lines. The right hand version has a size of 3 because the top half has 1, 2, 3 lines in the greater than or less than greater than bracketed areas. So is there a way that we could structure the code so that we could easily scale and be able to generate both of these figures by using methods and passing parameters? So one potential option is to make a variable to represent the size in the main function and then use the variable's value in all of the methods. However, if we were to do this, the variable which is in the main wouldn't be available in each of the other methods. So we would need to either pass parameters or use a class constant. That was my way of reminding you about variable scoping. So a variable that is declared in the main does not exist in the scope of another method. So rather than using parameters to resize the mirror, let's use a class constant. And let's have a class constant of 4 for the left-hand mirror and a class constant of 3 for the right-hand mirror. Obviously, a different version of this program could be accomplished by prompting the user for the size they would like and then implementing this as a parameter that is passed into the individual methods. That's something that you can do on your own for extra practice if you so wish. So first of all, the easy part is declaring the class constant. Public static final. Final is an important word here, which tells that this is a constant. Int size. So int is the data type, obviously. Size is the name. And we always put the names of class constants in all caps with words being separated by underscores in the name. We set it equal to 4. And now this variable uppercase size is known to all the methods in this class. Everybody knows and is able to access the value which is stored in size. So our main knows, our top half method knows, our bottom half method knows, everybody knows, every method which is a part of this class has access to the class constant size. Now the harder part. We're going to need to modify our loop in each of the sections of the top half so that we are able to generate the appropriate number of spaces and dots based on size. So for size 4, on line 1 we have 6 spaces and 0 dots. Line 2 we have 4 spaces and 4 dots. However, for a size 3 mirror on line 1, we would have 4 spaces and 0 dots. So we need to derive some formula for finding the number of spaces and dots given the variables line and size. One interesting thing is that it seems regardless of size, the number of dots stays the same. So for size 4 on line 1 we had 0 dots, on line 2 we had 4 dots. Well, for size 3 on line 1 we had 0 dots, and on line 2 we had 4 dots. So it seems like dots doesn't actually have to change with respect to size. And if we write out the formula to be able to achieve what we wanted, to make the number of spaces a formula which uses independent variables line and size, then this is what we get. Minus 2 times line plus 2 times size. So for size 4, we have minus 2 times line plus 2 times size. So minus 2 times line plus 8. So let's try it out. Line 1, so minus 2 times 1, negative 2 plus 8, 6. Yep. Let's try down here. So here we have 3 as size, so 2 times 3 is 6, so minus 2 times line plus 6. Line 1, minus 2 times 1 is 2, plus 6, 4, 4. Yep, seems to work. And as we said, we actually don't have to change the formula we were using to calculate the number of dots. Keep in mind, this is just one set of formulas which we could use to achieve the number of dots we need to draw and the number of spaces we need to draw. There are no doubt other ways that we could go about doing the same thing and get to the same answer. So now, the code for top half changes a bit. We have our class constant declared in the top of the class, and our top half method becomes as follows. We have the entire thing surrounded in a for loop, and this whole for loop is going to execute size times. So in this case, 4 times. So everything in here, from the first statement through the last statement, will execute 4 times. The reason, because we initialize our loop to have a counter variable called line with a value 1. We count up by 1 at the end of each loop, and we continue until this Boolean expression is false. And it becomes false when line becomes 5. So it's true for the numbers 1, 2, 3, and 4. So we're going to execute the internals of this loop 4 times. You should get good at reading for loop headers or for loop declarations, because it's a good skill to have. You should be able to look at a for loop and know pretty quickly how many times it's going to execute. So the internals then of this for loop are similar to what we had in the previous version of it back in the last lecture. We print out a bar, then we print out a number of spaces. Specifically in this case, we have a for loop to print out the number of spaces. And this for loop is going to initialize its count variable called space to 1, and it's going to count up until this Boolean expression is false. This Boolean expression should look pretty familiar. It's the formula we just derived on the previous slide. So this is the number of spaces we need to print. So the number of spaces we need to print is equal to the number of times we need to execute this loop. So we want to have this Boolean expression be true for all numbers less than or equal to negative 2 times line plus 2 times size, counting by 1. So at the end of each loop, we are going to increment by 1. And that will print out the appropriate number of spaces such that we wind up with the left-hand spaces for the mirror. Then we print out the less than, greater than. Then we print the dots. Now remember, we said the dots actually didn't depend on size. We're always going to do 4 times line minus 4. So this is precisely the same as the for loop we used on the version of this from the previous lecture. We print again less than, greater than. And then finally, we print out the exact same number of spaces again that we printed above. So that's the exact same loop duplicated down here. Again, if we were trying to further reduce redundancy, we would probably build this into a separate method where we could pass it the number of spaces we wanted it to print out. And then we would just calculate the number of spaces we wanted and pass that number in. That would be a little bit more readable, and I would advocate strongly that if this were code you were writing for a project or a programming assignment to be turned in, that you would do it that way. And then we terminate it with bar, and the code has fully printed one line of the mirror. The full code for this mirror printing exercise will be posted on Brightspace. So see Brightspace for the complete code. So some things to note about that solution we just showed for the program. First of all, our constant didn't replace all the uses of fors in the program. It only replaced situations where we were explicitly wanting to make reference to this size value. So this isn't a replacement for typing the number 4. This is a way to make explicitly clear that we are basing a formula on the size which is stored in this class constant. So it would be very wrong for you to go through and everywhere that you have the number 4 replace with the word size, because that would be very misleading, because it is not true that everywhere you wanted the number 4 to occur, you wanted to use the size. What if we changed the size to 3? Do you really want all of those locations in the program to go from 4 to 3? What if there was actually a place where you really needed the number 4? So don't think of class constants as a way to not type integer literals into your program. That's not accurate. What it is a way to avoid magic numbers. Remember back when we had the receipt program, we had the tax value and we were just multiplying by this, this random 0.08, and then we were multiplying by this random 0.15, and it was sort of unreadable. When I say unreadable, someone coming to it without already knowing what the program did couldn't have looked at the code and immediately known, oh, you're finding the tax and you're finding the tip. So it wasn't transparent and readily readable. By integrating class constants, we made it to where it was obvious what we were attempting to do. That's the same thing we did here. So we are eliminating these magic numbers that we just are using without any explanation or understanding of why. As a further disclaimer and reminder, don't create global variables at the class level. Global variables are considered very bad style. Does that make sense? Do you understand why global variables will be considered a bad style? The answer is twofold. Number one, it makes your code not modular. But some people might say, well, the same thing occurs with a class constant. Yeah, somewhat true. The other reason that global variables are considered very poor style is because it gives a way for a method to influence other methods' execution at runtime. Consider a situation where we had used a global variable for size instead of a class constant. In that case, we would have been able to change size in the program if we wanted to. Okay, so we changed size in the middle of one of the methods. Now all the other methods use size and execute differently because of the decision made in another method. So this is problematic because it means that your methods become more interdependent and more difficult to understand how they work. So this is a bad thing because it makes the readability and the maintainability of your code go way down. So now let's talk about using chars inside of a for loop. So recall characters in Java, so char type values are actually integer values under the hood. They're just interpreted as an ASCII encoding. We've looked at before that we can actually add an integer and a char and print out the value which results, and it is an integer. We can also typecast it to a char, and it will give us the char for that ASCII value. So we can also use chars in for loops. Consider if we wanted to print out the alphabet. An easy way to do this, rather than having to, know the ASCII value of A and, typecast and those sort of things, it'd be a lot easier to just declare your loop counter as my char and initialize it to the character lowercase a. Then your test would be my char less than or equal to lowercase z. Notice we're using single quotes because these are char literals, not string literals. So a has a lower ASCII value than z, so this test will be true for all letters which are occurring in the alphabet before z, and including z. And then we can also use the increment operator on chars as well. So we can use plus plus, and that will increment to the next letter in the alphabet. And then we can print this out, and we will print out each letter in the alphabet in succession. Think this through, and if you have any misunderstanding as to why this works, look at an ASCII table and see that the ASCII value for A is 1 less than the ASCII value for B, which is 1 less than the ASCII value for C. So those ASCII values are the integers that are actually being stored. What happens is when Java prints it out, is it goes to that ASCII table and says, okay, what does this integer value represent in character language? So now let's look at a simple program that makes use of these loops using chars to implement something called a Caesar cipher. This is something you may have done, I don't know, as a kid, or different things. They used to distribute encoder rings and cereal boxes, and all they really were little Caesar cipher machines. So as a little background, a Caesar cipher is a simple encryption where a message is encoded by shifting every letter a given number of steps in the alphabet. So as an example, if you had an A and you encoded it using the number 3, then A would become D, H becomes K, X becomes A, Z becomes C. So it wraps around, you see? So if you get to Z, you wrap back to A. So a shift of 3, you start at A, B, C, D. So D is the third letter from A. So a sample run of a simple Caesar cipher program would prompt for a secret message. In this case, Nicki Minaj is not a fan of Cardi B. And the secret key is 3. The result is the following encoded message. And you can't read it, but there it is. So all that was done to this was incrementing each letter along the alphabet by 3. And we're able to decode it by decrementing each of those letters along the alphabet by 3. So we could do another one. Cardi B is not a fan of Nicki Minaj. Notice that Cardi B is encoded the same at the beginning of the word as the name is at the end of the word. As is Nicki Minaj, as is not a fan of. So how will we go about this? How will we go about shifting each letter in a message to yield the cipher? So how will we go about implementing this encryption method? That's really what we're doing here. We're using a very, albeit very weak, encryption method. Well, one way we could go about it is to go through the alphabet and calculate the encrypted version of each letter, and then replace every occurrence of the original letter in our string with the encrypted version of the letter. So we start at A, and if we use the number 3, we would know that the encrypted version of A would be D, and so everywhere we found the letter A in the secret message, replace it with the letter D. Well, that would work. So the string methods replace and replace all actually do very similar things. The difference is replace all is built to also use regular expressions, which we're not going to be dealing with in this course. So regular expressions are a more powerful way of doing a search. But for this reason, in this class, you should always use replace. And actually, replace has lower overhead since it doesn't have to implement all of the regular expression functionality. So we should already be able to write our main method. The main method is usually simple and should read like a summarization of the program in general. So we should be able to do that without even dealing with the complexities of this program. So step one, we'll declare a scanner object, use that to get input from the user, prompt the user for a secret message, get the next line of input from the user. It has a string stored in user message. Convert that string to lowercase so that we don't have to deal with both upper and lowercase characters, and store that into user message. So remember how objects work. We just made a string object and assigned the location of that object to the variable user message. But then down here, we went to that location and used the toLowercase method to make a new object, and now we have assigned this new object's memory location to user method. So the original string object is gone. And we have a new string object with all lowercase letters, which contains the same characters, just as lowercase, as the original message. Then we will prompt the user for a shift value. So this will be the value used to perform the Caesar cipher. And we do a next int and save that in our shift value. Then we're going to create some method which encodes the user message using shift. And we will get the encrypted string. And then we will print the encrypted string to the console. We were able to write that method, the main method, without even having to think through the complexity of the program, simply because it was obvious that the user interaction would take place followed by a method which would encode our string based on a shift parameter. So now let's look at this encode method. It's going to return a string value and accept a parameter of text and shift. Also note that it expects the shift value to be between -26 and +26. So if we use something greater than that or less than that, that would create problems. And there's a way we could pre-process their input to ensure that their shift was in that range. But we won't do that this time. However, we should note and document in comment form that the method expects the shift to be between -26 and 26. Inside this for loop, we have the declaration or header and the body. In the declaration, we have the initialization, the test, and the update. Our initialization creates a variable called ch and initializes it to the value a. The test is going to see if ch is less than or equal to z, and we're going to increment by 1 for an update. This will loop through the alphabet, just like we've talked about. So we're going to create a variable inside this loop called, now remember, it's inside the loop, so it disappears as soon as we exit the loop and go down to the statements after the for loop. So this variable is only in existence inside this for loop. That's the scope of the variable. So we declare this variable, which is of type char. We call it new ch, and we initialize it to the value of the current character. So we're looping through the alphabet one character at a time, so the current character plus the shift. So this is what A would become or what B would become. So let's look at the character A. So this is on the first iteration of our loop. If we're shifting by 3, A becomes D. So this would be our encoded version of A. and then on the next loop it would be the encoded version of B, and so forth. So this is going to yield an integer value. CH plus shift is going to yield an integer value because char plus int is going to result in an int. But then we typecast it into a char. So new CH is now D if our shift was 3 and CH was A. So this is going to shift just the letters. Anything that's not a letter is going to be left alone. And the way that we're going to accomplish that is if the new CH is greater than Z, then we're going to wrap back. So if we have A on the number line, so to speak, or letter line, and then we have Z, if this new character exists outside of that area, such as over here, then we will subtract 26 from it. So it would be char minus 26, and that would get us back over somewhere in here. Very similarly, if we were given a shift of a negative number and we wound up somewhere over here, we would say CH plus 26 to wind up back over here somewhere. So this little example is analogous to what's going on in this section of code. If new CH is greater than Z, so out here, we'll subtract 26 from new CH, cast that into a char, and put that into new CH. Else if, so it's not an else, it's an else if, new CH is less than A, so it's out here, we'll add 26, cast it into a char, store that into new CH. Next, we need to convert this encoded version to an uppercase letter. So there's two ways you could go about this. A very quick and dirty way to do a conversion to uppercase would be new char minus the quantity A minus uppercase A. So this figures out the difference between an A and an uppercase A and subtracts that from the new char and then casts that into a char. That would convert to uppercase, but that's for you to figure out how that works. You don't have to use that method at all, and I wouldn't recommend it. The method I would recommend is to use the character class and use the method to uppercase in the character class and give new CH as the parameter to that method. This will give the uppercase version of new CH, and we will cast it into a char just for good measure, and we pass it to the replace method in the string class. So text contains our string that the user typed in that they wanted to encode. So we're going to replace in text everywhere that we find CH with the uppercase version of the encoded. So if we were doing the first loop through this, everywhere we found a lowercase a, we would replace with an uppercase D. You may be wondering, why are we replacing with an uppercase D? Well, that's because if we were used a lowercase d, then we would again replace it when we got to D in our progression through our loop. Consider if our string we wanted to encode was just the letter A, lowercase letter A, and we're going through every letter in the alphabet. So we get A, and we encode it as D. So A becomes D. Okay? Then we go to B, there are no B's, so nothing changes. We go to C, no, there are no C's, nothing changes. Oh, CH takes on the value D. Well, the encoded version of D is going to be F, and we have a D. And so we would then convert this D to an F. and that's not at all what we want. Once a letter has been converted, we only want to convert it once. So to do this, instead of replacing it with the lowercase version of the letter, we'll replace it with the uppercase version. This helps us because when we search for CH, which is lowercase d, so let's erase this and write down what we have instead. We replaced our lowercase a with an uppercase d encoding. Now, when we get to CH having the value lowercase d, and we do a replace all lowercase d with the letter lowercase, or with letter uppercase f, we don't find any lowercase d's in this string, and we don't replace it a second time. So this will go through and replace each letter in succession that is present in this string. Finally, after the string is completed going through every letter in the alphabet and encoding our secret message, when the CH value becomes greater than Z, so it gets out here on the letter line, our program pointer will jump down to the statement immediately following the for loop and return the string text.toLowercase. So it doesn't return the string in text, it actually returns a new string which is generated by converting all the letters in text to lowercase. So it builds a new string object and returns the address to this new string object back to our main function. Something that you'll use loops for, no doubt, many times in your time as a programmer is cumulative sums. If you need to have a way to add up, say, all the numbers from 1 to 1,000, loops are a good way to go about that. If you declare a sum variable outside the scope of the for loop so that you have access to it outside the scope of the for loop, then you declare a for loop that counts from 1 to 1,000, and you add each of those numbers together and store it in sum. This would give you the sum of all the numbers 1 to 1,000. A related problem to the cumulative sum problem is needing to find the minimum or maximum value from a set of numbers. And this is a common problem in computer science that you'll run into from time to time. The general approach to solving this is for each number you compare it to the current best. So if we're trying to find the minimum, you compare it to the current minimum to see if it's smaller. If it is smaller, you assign that value as the current known minimum and continue through the rest of the set. So here's an example code snippet that will prompt a user for 100 test scores in succession and find the max test score in that set of test scores. So obviously, to be able to get user input, we need a scanner. We're going to call it console, and we are going to initialize our max variable outside the for loop because we want to be able to use it outside the for loop. So we're going to create this integer called max and set it equal to -1. We're going to set it equal to -1 because we know that there will be no test score lower or even as low as -1. So in this way, we have appropriately initialized our maximum value so that even if the max test score was 0, we would still accurately find the max test score. So then we have our for loop, which we initialize I to 1, and we test to see if I is less than or equal to 100, which will, since we're counting by 1 in our update, this will make us do the contents of the for loop 100 times. And inside this for loop, we prompt the user for a test score and then get the next integer from the input stream. So the user types in an integer, and that goes into the variable score, which we declared somewhere up above in the program. And we check to see if score is greater than max. So what we're considering is this latest score that has been typed in the new highest test score? And if it is, then we replace max with this score. So since max started as -1, the first time through this loop, the user will type in some value, and even if it's 0, then score will be greater than max, and max will be assigned the value score. So max would now be 0 if score was 0. And this will happen 100 times. So we're going to prompt the user 100 times for test scores, and then we will display afterwards what the max test score was in a print line statement. Finding the maximum of test scores is easy in one way because we know the range of values for a test score. So we knew that it was appropriate to initialize our max to -1. But what if we didn't know what range that we were dealing with? So what if someone said, find the maximum of the wavelet transform value for the test score? Well, unless you're familiar with what the wavelet transform value's range is, you don't know what an initialization, what initialization would be appropriate to find the max. Because let's say that wavelet always exists between -10 and -1. Well, if you happen to have initialized your max to -1, then you'll never find a value greater than that. By the way, the wavelet does not have a range of -10 to 1. That's just an example, or -10 to -1. So the answer to this situation where you don't know the appropriate range is, instead of initializing your max to some lower bound, instead initialize your max to the very first number in the set. So now, if we did that with our test maximum program, whatever the first thing the user typed in happened to be, that would be our initial maximum. And that would be okay, because if we never found anything higher than that, that was the maximum. So that would work well too, is assigning the first number in the set to the maximum and then comparing everything to it. What if we don't know how many numbers the user is going to enter? So like in the last slide, we said, well, we're going to do this 100 times. The user is going to enter 100 numbers. Well, if we don't know how many times the user wants to enter a test score, so they just want to enter all their test scores, and that may be 10, 20, 71. If we don't know how many they're going to want to enter in, then instead of doing a count loop, we really want to do an event loop. And in this case, we would exit the loop when a certain event occurred. An example of this would be enter a test score or enter -1 to exit the program. In this way, the user can continue to enter scores until they are done entering scores and they type in -1, and then it exits the loop and prints out the maximum. So far we've primarily dealt with these counter loops, where we knew how many times, or we were able to calculate how many times we wanted to do something. Examples of this would be if we wanted to print hello 10 times, or find all prime numbers up to some integer n, or print each odd number between 5 and 127. These are count situations where we check every number between 5 and 127, and once we get to 128, we stop. These are counter loops. On the other hand, an event loop executes until some condition becomes false. And in this situation, the actual number of times that the loop will execute isn't known beforehand. So knowing something beforehand is often referred to as knowing it a priori. We don't know a priori how many times this loop is going to execute. We just know we want to do it until something happens. And we will code that something into a Boolean expression, and when that Boolean expression becomes false, then we know it's time to quit the loop. So what would be some examples? If we wanted to prompt the user until they had typed some non-negative number. So what I'm saying here is, let's say that you said, hey, type in a non-negative number, but the user typed in a negative number. Then you want to do it again. So you want to continue to prompt them until they type in a non-negative number. Or maybe you want to print random numbers until a prime number is printed. So since we can't predict what the random number generator is going to print out, we will print random numbers, and we're going to keep printing random numbers until we have printed a prime. When we print the prime, we're done. So this is a repeat until something happens. Typically, we use for loops for counter loops. On the other hand, we would typically use a while loop for an event loop. The while loop has a different structure which lends itself a little better to coding event loops, and it's easier to read while loops when the test condition isn't so simple as when we get to a number that is greater than 5, stop. So let's look at the execution and the syntax for a while loop. While loops actually look extremely like a for loop when we look at their function diagram. So we test to see if something is true, if some test is true. If it is, we do some statements, and then we move on. And we test to see if it's true again. If it is true, we do the statements again. Is it still true? Then we do the statements again. Is it still true? We do the statements again. Until, is it still true? No. Then we move on and exit the loop. The syntax, the keyword while, followed by parentheses, and inside the parentheses, we place the test. This is a Boolean expression, just like it was in the for loop, just like it is in an if statement. However, an if is not a loop. An if is a way of controlling the flow of the program. It's a way of deciding if something should or should not occur, or deciding between multiple things occurring. Whereas a while loop is a way to make something occur multiple times. So here's an example use of a while loop. Initialize some number to 1, and we call that number num, and then we say keyword while, and then we have our Boolean expression for the test. So as long as this test is true, we will continue to execute this loop. So num less than or equal to 200. Yep, that's true. So we're going to do it at least once. So we print out a space. We print out num followed by a space. So we print out 1. We multiply num times 2, store it in num. We have hit the end of the loop. While loops are a little more simple. We don't have to do the update and initialization. So if you want to initialize something, you have to do it yourself. If you want to update something, you have to do it yourself. Once we hit the end of the loop, we come back, we test again. Num is now 2. Is 2 less than 200 or equal to 200? Yes, it is. So therefore we do the loop again. And we do that until we get to the number 256, at which point this becomes false, and the program pointer will jump to the statements immediately following the while loop. One more time for good measure. The while loop and if statements look similar. They only have one difference. That's the word while versus the word if. They are very different. If statements choose to do or not to do something. While loops choose how many times to do something based on the test condition. There is no way to make an if statement repeat without using a loop with it. So they are very, very different. They're not to be confused. Do not refer to an if loop. If you do, then I will claim you never took this class. Now let's work through some examples to better understand how the while loop works. So take a moment, pause, and write a while loop that is equivalent to this for loop. Okay, so I'm going to reveal the solution and we'll talk through it. So the for loop initializes a variable I to the value 0 and tests to see if I is less than 10 and updates by 1 each loop. And it prints out the value of I each time the loop executes. So this will print out the values 0 through 9. It's not inclusive of 10. Be careful about that. It's important to notice whether or not the test condition is inclusive or exclusive. This is 0 to 10 exclusive of 10. So that would be printing out 0 through 9. Well, we can directly take these sections of code, the initialization, test, and update, and put them into a while loop format. The initialization has to go above the while loop. So we create a variable I and initialize it above the while loop. The test goes into the test of the while loop, so is I less than 10. And the update goes in as the very last statement in the while loop. The body of the for loop becomes the body of the while loop. So we have programmatically transformed this for loop into a while loop, but now let's work through it functionally. We execute top down, so we declare this variable I as an integer and assign it the value 0. Then we enter the while loop if I is less than 10. If not, we just jump to the end and move on. But it is less than 10. 0 is less than 10, so then we do the statements inside the while loop. We print out 0 and then increment I. So I is now 1. Go back and test. Is 1 less than 10? Yes, it is. Print out 1, 2, 3, 4, 5, 6, 7, 8. And then at 9, this will print out 9, increment to 10, and it tests to see if 10 is less than 10. The answer is no. So at this point, the program pointer will jump to the statement immediately following the while loop and continue executing there. Look at this code in this while loop. Will it compile? And do you think it will run correctly? So it's supposed to locate the first uppercase character in a string, which is input by the user. So it's going to return the index of the first uppercase letter in this string. So let's look at the code functionally. First of all, to be able to get input from a user, we have to have a scanner object. We're going to prompt the user for input, enter the string, and then we are going to do a get next line, or just next line from the console. So console object dot next line is going to get the next line of input from the input string and store that into a string called user string. Then we declare a variable called I, initialize it to 0, and we are going to test to see if some character is uppercase. Or rather, we're going to test to see if it's not uppercase, because this code is funky looking, so it's hard to tell exactly what's happening. And it has a syntax error. So we have user string, which is a type string, and we're using the .charat method, and we're getting the char at the index starting at 0 up until we find an uppercase letter. And then we're saying .is uppercase. Hopefully you realize that's bad. This method, so this is an object, and this is a method of that object. So this is going to return a char value. Char values are not objects. We cannot call methods using the dot operator on char values. So this dot is uppercase doesn't work. So that's the first problem I see. The second problem is, what happens if the word has no uppercase characters? Then this loop is just going to continue until, well, forever. Actually, it won't. What it'll do is it'll continue until the index I goes past the end of the string, and we're going to attempt to access a memory location that doesn't exist. That'll be a runtime error, and the program will crash. So let's fix these errors. First of all, rather than attempting to use a method via the dot operator on a char value, what we need to do is use the character class, which is a wrapper class for char values, and use the isUpperCase and provide the char as a parameter to that method. Then we also need to not use the is=false in our Boolean expression, because that's clunky and not very readable, and so it would be much better to use a more readable approach to that Boolean expression. So let's fix these. So here's the revised code. Does it compile and run correctly? Declare the scanner object console, prompt the user, get a line of text, initialize I to 0. Now we are going to say while character.isUpperCase, so we're using the character wrapper class and the isUpperCase method of the character wrapper class to get a Boolean value returned telling if the current character is uppercase. So if it is not uppercase, then we are going to continue our loop. And what we're passing to isUpperCase is the char at index I in the user string. That works pretty good, but we didn't fix our implementation error, where if there are no uppercase letters, we are going to continue until I is greater than the length of the string, and we attempt to access, position 13 on a string that is only 12 characters long, and boom, crash goes the program. This situation where there is no capital letters would be an edge condition. So to test a loop properly, or to test any code properly, you really need to test all the edge conditions. In this situation, the edge conditions would be a capital letter in the first or last position, as well as a capital letter in any of the mid positions, as well as unusual scenarios like multiple capital letters and no capital letters. If all of these pass and succeed, then most likely your code is complete and accurate. So we've discussed that we need to deal with the situation where there are no capital letters, but we also need to deal with one other little thing. Users who are not programmers often are going to find dealing with a zero index string confusing. So they're used to thinking of the first index of something, or the first position, being 1, not 0. So to make this more seamless and usable by most people, we will start counting at 1 rather than 0. Maybe a solution we could use to prevent the program from crashing when there's no capital letters would be to also check to see if I is less than the user string length. That's a good thought, but this code will actually still crash the program. Think about why. If you thought of short circuit evaluation, then you're absolutely right. This Boolean expression will be evaluated first. If it's false, then none of the rest of the Boolean expressions will be evaluated. However, that still means that when we attempt to access the 13th position in a string that only has 12 characters, and we're attempting to find out if that is an uppercase letter or not, we're still attempting to access that memory location, and the program still crashes. For this to work, we would have to have the string length comparison occur first. And then if this fails and is false, since the logical AND operator uses short circuit evaluation, none of the rest operands in the logical AND will be evaluated, and therefore we won't attempt to access a memory location that doesn't exist. So here we fixed that ordering issue. So now we're checking to see that I is less than the length of the string before we attempt to access the char at location I, or index I. So now, when this is false, we are going to short circuit this logical AND operator, and we won't attempt to access a non-existent memory location. So that's good. Then also, when we go to print out our location of the first capital letter, we have the option to print out that there are no capital letters if our index is equal to the string length, which would be the situation where we've checked every position and there are no capital letters. However, if I is less than string length, then we know that we have found a capital letter and it occurred at index I. But to make that more familiar to users that don't understand that strings are zero indexed, we'll print out I plus 1. So, if we were talking about the very first element in a string, then that would be position 0 or index 0, but we would tell the user it was 1 because the user doesn't need to understand how Java is indexing strings. So sometimes we hide some of the implementation for the purpose of making things easier for consumers or users. So an interesting thing about for loops is that when Java compiles a for loop and compiles a while loop, it compiles into the same thing. Fundamentally, a for loop is actually a while loop. And therefore, anything you implement as a for loop can be implemented as a while loop and vice versa. However, even though they are interchangeable technically, often the code is more readable when you make the appropriate choice. So if you're doing a counting situation where you know the number of iterations that you need to occur, a for loop is best. See, down here in this while loop where we implement the same functionality as the above for loop, the functionality is not as obvious. So don't get in the habit of always using a while loop for everything. Use for loops when you are counting or doing a counting loop operation and the number of loops is known. One important use that I mentioned earlier of while loops is data validation. So if you tell a user, enter a non-negative integer, and they type -5, it would be good to be able to continually prompt them again until they enter a non-negative integer. So we can write a code segment using while loops with a test to see if the integer is negative or not. The integer which the user types is negative or not. And if it is negative, then we'll just loop and prompt them again. And we'll continue this loop until they type a non-negative integer. So here's a code snippet that does exactly that. We prompt the user for a non-negative integer, and we get the integer from our scanner. Then we will check to see if that number is less than 0 using a while loop. So while the number the user entered is less than 0, prompt them again, and this time you might want to enter some sort of a error message saying like invalid number or something, and you get the next integer that they type into this number variable. At the end of the loop, we will test number to see if it is less than 0. If it's still less than 0, we prompt them again, and this will go on until they type something that is non-negative, at which point this test will fail, and we will jump to the next statement after the while loop body, at which point we print out the square root of number is, and then the square root of the number. So if we were not allowing imaginary numbers, performing a square root operation would be a situation where we would not allow a user to type in a negative integer. So we would need to perform this sort of data validation to ensure that the user typed in a positive integer. So we had previously introduced the idea that certain things that the user types in may cause a program to crash. And we said that if a user provides garbage into the program, then garbage comes out of the program. So this idea of data validation using while loops and testing what the user has typed in is precisely a way to test and ensure that what is given is not garbage. So as a final while loop exercise for this lecture, let's write a method called digit sum that accepts an integer as a parameter and is going to return the sum of all the digits. And you can assume that the number is non-negative, which the user enters, so we won't do data validation on it. So as an example, if the user typed in 29,107, then the method would return 19, because that's the sum of all those digits. So consider this. Does it matter what order we process the digits in? Would a different order make the problem easier? How do we extract the last digit from the number? How do we delete a digit from the number to make it smaller? And how do we know we're done? So here's a solution to this problem. We declare public static, and it's going to return an integer value. The name of this method is digit sum, and it accepts a parameter n. We need to have somewhere to store the running total, so we'll call that sum, and we'll initialize it to 0. Now, what we're going to do is we are going to take the last digit of n, and we're going to add that value to sum. And then we are going to remove that last digit. So given the number 213, we are going to take 3, add it to sum, and get 3, which will leave us with 21 in n. Then we are going to remove 1, add it to sum, which gives us 4, which will leave us with 2 as n. Then we'll take 2, add it to sum, which will give us 6 in sum. And now the value of n is 0. So to implement this, we say while n is greater than 0, and to get the rightmost digit, we simply do n mod 10 plus equals is a shorthand operator to add this value to the value currently stored in sum, and then store this resultant into sum. So in the case of 213, we would have grabbed the 3 and added 0 plus 3 and stored that into sum. So sum would be 3. Then we would do integer division. So n divided by 10. If n is 213, 10 goes into 213 exactly 21 times, and the remainder is dropped. Not rounded, it's truncated. So 21 would be the new value of n. Then we are at the end of the loop, so is 21 greater than 0? Yes. So then we would do 21 mod 10 results in 1. 1 plus 3 gets stored into sum, that's 4. We would then divide 21 by 10. That will give us 2 with a remainder of 1, but we drop the remainder. So n is now 2. We have hit the end of the loop. Is 2 greater than 0? Yes. 2 mod 10 is 2, which will be added to the 4, which is already stored in sum, gives us 6. Then 2 divided by 10 is going to give us an integer result of 0 with a remainder 2. But the remainder is truncated, and so n has the value 0. Is 0 greater than 0? No. So the program pointer jumps down and returns sum. Now one thing, does it matter that the method changes the value of n? Remember we said when we pass an object, that's actually a reference to an object stored in memory, and so if we change it inside the method, then when we go back, it'll be changed outside the method. What I just said is true. However, n is not an object. It is an actual integer value. So native or primitive types, such as integer, double, char, not string. String is an object. But these primitive data types actually store the value in the stack memory, which is where we keep our variables. So this n actually contains the value rather than containing a location for where to go find the value. When we deal with objects, as we've already been over, we have the object in heap memory, and the variable only stores the memory location